Hello class, welcome to this lesson on 5.1, starting the new section for the new unit on roots, radicals, and rational exponents. Right, so what we want to address is how are exponents and radicals used to represent roots of real numbers? We want to be able to relate roots and rational exponents and use to simplify expressions and maybe solve equations, but if not, we'll probably push it to another lesson. So the vocab in this unit includes the index, the nth root, the radical symbol, and radicand. So we're going to briefly discuss nth roots. So you may remember what the square root is. So we're going to go briefly demonstrate that. So let's look at the following problem: x squared equals 25. So you may remember how to solve this equation. We need two numbers that when we multiply by themselves, twice, gives you 25. Well, in that case, you could say that x is equal to 5, right? You could say that x is equal to 5 because 5 times 5 is 25, or 5 squared is equal to 25. And by that same reasoning, you could also say that x is equal to negative 5 as well, because negative 5 squared is negative 5 times negative 5, which is positive 25 as well. So this solution has two equations, or two roots, and we call those two roots 5 and negative 5. So these are my two roots, my two real roots. So these are called square roots in this case because it's based off of a square equation. So in other words, another way to solve this is to take the square root of both sides. So that's what we have a symbol for here, like this, right? So we take the square root of that side and then we take the square root of the other side. Now, we know now that this right here is the square root symbol, right? More specifically, this symbol is called a radicand, or a radical symbol, I'm sorry, radical. So that symbol is called a radical. And this is going to be used to, this radical symbol is going to be used for all the roots that we're looking at, okay? So in this case, this radical is called the square root. So in this case, well, we know that the square root of x squared is just going to be x because x times x is x squared. And then the square root of 25, well, we just said that the square root of 25, well, we know that 25 is 5 squared, or 5 times 5, and therefore we know that the square root of 5 squared is 5. So you can think of the squared and the square root as canceling out in this case, leaving you to the result of 5. Now this square root right here that we just found is called the principal square root. Principal square root. And it's called the principal square root because we're looking at the positive answer in this case, not the negative answer. So we're only looking at the positive roots, if you will. In this case, positive 5. Right? So the principal square root of 25 is 5. All right. So now another thing that we want to show you is, let's look at a similar example to the equation we just looked at here. So let's look at x cubed equals 125. So similarly, we want to figure out a number that when we multiply by itself 3 times, gives us 125. If we want to use the symbols here to solve, just like we did with the square root symbol, well, we can also get rid of the 3 with some kind of radical. What kind of radical? Well, we can get rid of a cubed, so this is x cubed. We can get rid of it with a cube root. Again, this symbol with the radical and the 3 on top is called the cube root. So this is the cube root symbol. All right, so again, let's recap. This symbol is called the radical. This symbol, this 3 right here is called the index. And the number that is inside the radical, so the number inside is the radicand. So we got a few vocab terms here. Index, radical, and radicand. So again, the index for the cube root is 3. The index for a square root is an invisible 2. Invisible for a square root. So for the square root, the index equals 2. For the cube root, the index equals 3. And for the 4th root, 5th root, 6th root, the index would be 4, 5, and 6 respectively, and so on. So then let's go back to the problem at hand. Now that these 3's match, we can cancel them out. And basically the entire radical cancels out, leaving you with simply x equals the cube root 125. So we need a number that when we multiply by itself 3 times gives us 125. Well, we know that 125 breaks into 5 times 25, and then 25 breaks into 5 times 5. So lo and behold, it looks like 125 can be broken into 3 5s. So therefore, this can be written as the cube root of 5 to the 3rd power. And now we can think of the cubes as simply canceling out, leaving us with the result of 5. And the radical symbol cancels out. So notice that when you the answer is only going to be 5. If you were to try negative 5 to the 3rd, well, negative 5 to the 3rd is negative 5 times negative 5 times negative 5, and that will give you negative 125, not positive 125. So using a negative number here doesn't work like it did with the square root. So therefore, when you're taking the cube root or 5th root or 7th root, anything that is odd, then you're only going to have the positive result, or you're only going to have the one answer rather, not 2 answers. All right, so now we know that this x equals 5 in this problem is the real cube root of 125. So let's generalize this a little bit. So let's say we had x to the n, instead of it being squared or cubed, let's make it n, equals some number c. In this case, if I were to want to solve for x, right, I would have to take the nth root of both sides. I had to make sure that those numbers match. And then I would have to do the same thing on both sides. So again, this radical with the n here is known as the nth root. And now in this case, the result cancels on the left side, leaving me with x equals the nth root of c. Again, c being the radicand, this being the radical symbol, and n being the index. All right. So go ahead and try the following problem. See if you can solve x to the 4th equals 81, x to the 3rd equals 64. Pause the video and we'll solve it in just a sec. All right, hopefully you paused the video and gave the problem a try. So let's go ahead and look at part A. So we have here x to the 4th equals 81. So we need a number that when we multiply by itself 4 times equals 81. All right, using the symbols here, just so that we can get a little bit of practice with the notation, Let's go ahead and get rid of the 4 here by doing the radical with a index of 4. So now we're going to take the 4th root of both sides. That's how you say that, the 4th root. And then you're going to do the same thing on the other side. Now, when we take an even power, this is even, right? When we do an even power, we want to make sure that we include the plus or minus. So we're going to go ahead and include a plus or minus in our result, like that. Why do we need to include a plus or minus? Well, remember that for the problem where it was 5 squared equals 25, we knew that negative 5 squared was also 25. So when you have an even power, make sure to include the plus or minus. Okay, so we'll put that as a little note. So if you have an even index, make sure to include the plus or minus. All right, so now we have the fourths cancel, leaving you with x equals plus or minus the 4th root of 81. So we need a number that when we multiply by itself 4 times gives us 81. Well, we know that 81, let's go ahead and break that apart. 81 is 9 times 9. And we can break 9 into 3 times 3. Those are primes. We can break 9 into 3 times 3. Again, we got another 2 prime numbers. And look, at lo and behold, looks like we have 4 3s. So this can be written as 3 to the 4th. So we're going to write this as x equals plus or minus the 4th root of 3 to the 4th power. And now notice that the 4th power and the 4th root simply cancel. So leaving you with x equals plus or minus 3. All right, let's look at the second problem. So again, we need a number that when we multiply by itself 3 times gives us 64. Using the appropriate symbols, let's go ahead and take care of this cube by doing a cube root on both sides. Now, since this is odd, you don't need to include a plus or minus, okay? So only for evens will you include a plus or minus. So in this case now, the cube root cancels with a cube. So we have x equals cube root of 64. So we need a number that when we multiply by itself 3 times gives us 64. If you're having trouble with this, go ahead and factor the 64. So 64 breaks into 4 times... well, let's do 8 times 8, because 8 times 8 is probably the most consistent example for students. And 8 is 2 times 4. So we got a prime here. 4 is 2 times 2. And then we have 8 here is 2 times 2, or 2 times 4 rather. And then 4 is 2 times 2. So now what we're looking for is we need a number that can be written as itself 3 times. However, notice that we have two sets of 3's here. We have a 2 to the 3rd here, right? And we have a 2 to the 3rd here as well. So how do we go about writing that? Well, since we have 3 2's there and 2 sets of them, I'm going to go ahead and write this out as cube root. Now I have this 2 to the 3rd power here, right? So I have a 2 to the 3rd here, and I got another 2 to the 3rd here. So I'm going to go ahead and write those out next to each other. 2 to the 3rd times 2 to the 3rd. And so I got basically, 2 sets of 2 to the 3rd. So what I can do is I can split this radical into 2 separate things. One for this 2 to the 3rd and the other one for the other 2 to the 3rd. And so now I got, well, this 3 cancels out here with the radical, and then this 3 cancels out with the radical here. So I'm left with basically 2 times 2, which is 4. So essentially when you're factoring the number, the index tells you how many of that number you're looking for. So if in this case you're looking for 3 of that number, if you're looking for 3 of that number, then you're going to simply pull that number out of the radical and kick it out. You can also you can think of it that way. And then so we kicked it out twice, and therefore we got 2 times 2, which is 4. So there's different ways that you can think about it, but this is a way to use this with rational exponent or with exponent properties. All right, so now we're gonna talk about rational exponents. So what are rational exponents? Well, remember that the word rational means fractional. So when we mean rational exponents, we mean fractional exponents. And you might be asking yourselves, when will we use exponents that are actually fractions? And what does it mean to have an exponent that's a fraction? So we're going to actually demonstrate that with this example. So what we want to do here, our goal is we want to be able to rewrite the square root of x, since now we talked about square roots in this example and cube roots and so on. We want to be able to write them in terms of exponents. So that's exactly what we're going to do here. So let's say we have square root of x, and we want to write this as a x raised to some kind of power. Now, if you're well versed in fractional exponents, you already know what this answer is. But we're going to go through this example regardless. So we need to figure out what the exponent is that is equivalent to the square root of x. So in order to do this, we're going to actually solve this. So since this is a square root, remember that the index is an invisible 2. So the only way to get rid of it is to basically square both sides. So if we square that, well, now we got x squared and then we got square root. So now the square root and square cancel. Just like in the other example when we had cube root of x cubed or square root of x squared. Now if you do it to this side, you got to do it to the other side. So now we have x equals x to the, now this is n times 2 here. If you have an exponent raised to an exponent, you're just going to multiply those two exponents here. So this is really n times 2, which is 2n. All right, so now we have x to the 1 power, there's an invisible 1 power there, equals x to the 2n power. Well, if you think about it, logically, this means that the 1 power has to equal the 2n power because these two x's match. So what we're going to do is we're going to set the exponents equal to each other. So 1 has to equal 2 to the n. So we're going to set that equal, or 2n. So 1 is equal to 2n. We can go ahead and solve for the exponent n by dividing by 2 on both sides. And so now we're left with n equals 1/2. So what this means is that we can write the square root of x simply as x to the 1/2. So what does it mean to have a fractional exponent? Well, a fractional exponent means that it can be converted to a radical. So you can go back and forth between a radical and a rational exponent, which is a pretty interesting result. So let's look at another example of this. So let's say we wanted to convert the cube root of x in terms of an exponent. Well, how will that look like? All right, well, we're going to do the same process here. Since we got a cube root here, the only way to get rid of it is if we have a cube. So we're going to go ahead and cube both sides. And so now we got x cubed to the cube root. These, match so they can cancel. So we have x equals, and then we got to multiply these two together, these two exponents. So that's going to be x to the 3n. And so now we got an invisible 1 here. So we can say that the exponents have to be equal to each other. So we know that 1 has to equal 3n. We divide by 3 on both sides. And we get the n is 1/3. Which means that the cube root of x is equal to x to the 1/3. Okay, so now we know that the square root of x can be written as x to the 1/2 power. And cube root of x can be written as x to the 1/3 power. What about, something like, that's a little more complicated? So let's look at one more example of this. So let's say we had cube root of x squared equals what? So what can that be written as if you have a squared and the cube root? Actually, just to make things more interesting, let's make this a 5. What happens if we have a 5 there and a 2 there? Well, let's go ahead and solve this out. Well, we got a 5 here, so we know that we can get rid of that by raising it to the 5th power. So now we got 5 and 5 match, so they can cancel. So now we have left with x squared equals x to the 5n. We can multiply these two results together. So now we know that the exponents have to match. So I know that 2 has to equal 5n. And so I can solve for n by dividing by 5. So my exponent n has to be 2/5. So that means that the 5th root of x squared is x to the 2/5. Interestingly enough. So what did we learn about this? Well, we know now that radicals can be written as rational exponents, and you should probably notice a rule here. There's some kind of rule that binds these three together. And so we'll go ahead and generalize that for you. So if we had a radical of n, well, notice that the index matches the denominator in each of these cases. So I know that if I have a radical with n, I know that it has to have a fraction with the denominator of n. Now, if I look at this example, I know that if I have a power of 2, that means I'm going to have a numerator of 2 in the power. Or if I have an invisible power of 1, that's going to show up as a 1 in the numerator. So if I have raised to the m power, well, then I know that this has to be m. So this is my final result. So this is how I can convert a radical into a fractional or rational exponent. So hopefully that made sense. I went ahead and actually summarize this again. X to the m over n power is equal to the nth root of x to the m. So again, the way to remember is power over index. So the power goes here. That's obviously the power, right? To the x to the mth power. And the index goes here. So power over index. So if you want to convert anything into a fractional exponent or vice versa, then you can use this to help you. So now, again, like we said, radicals can be written as fractional exponents. That was the main key here. So let's go ahead and evaluate these examples. So let's say we wanted to do 16 to the 1/4 power. Well, again, now we know that a fractional exponent can be simply written as a radical. So really, this really means, so this is my power. Remember, power over index. So this is my index. So if I want to write this as a radical, I'll have radical. My index is 4, so that goes here. I got 16 is my radicand, so this right here becomes my radicand. And then my power is 1, so it's 16 to the 1 power, which really I don't have to write. So now we basically have the 4th root of 16. So what number, if I multiply it by itself 4 times, gives you 16? Well, if I break 16 down, 16 is 2 times 8, 8 is 2 times 4, and 4 is 2 times 2, and lo and behold, I got 4 2's. So I can write this out as 4th root of 2 to the 4th power. And now that these match, I can cancel out, so I got an answer of 2. Now note here that we are simply doing the principal 4th root. So we're not looking at the plus or minus version here. We're not actually solving this. We're just evaluating, and they only want the positive version here. We're not doing the negative version here. Okay, so if they wanted the positive and negative version, they would have written a plus or minus here, but there is no plus or minus written there. So I don't want you to confuse that for solving. All right, so for part B, we have, again, power over index. So this is my power, this is my index. So I have here, my index is 3, so that's a cube root. I got my radicand is 27, and then I got a power of 2. So how do I go about solving this? Well, first I can do the cube root of 27. So I can write this out as cube root of 27 raised to the second power. And then I can focus on the cube root part. So what number, when I multiply by itself 3 times, will give me 27? Well, 27 is 3 times 9, and 9 is 3 times 3. So I got 3 3's there. So if I did 3 to the third power, that would give me 27. So I can rewrite this as cube root of 3 to the third power squared. And now I know that the cube roots and the cube cancels, and so I'm left with 3 squared. Well, what's 3 squared? That's simply going to be 9. All right, so part C, notice that we have a negative exponent here. What does that mean? Well, a negative exponent means that you're essentially doing the reciprocal or flipping the number. Okay, so a negative exponent means reciprocal, which means you flip the fraction. So you flip the number. All right, so that means that if we write 32 as 32 over 1 and we flip it, then it's going to be 1 over 32. Okay, so we can rewrite 32 to the negative 2/5 power. We can rewrite this as 32 over 1 and then flip it, and then so we get 1 over 32, and then we can do raised to the positive 2/5 power. So what I do is I call this the flip and forget method. So I call it flip and forget, which means you flip the fraction, right? So you do the flipperoo, and then you forget the sign. So you notice that we forget the sign. So since we forgot the sign, now it's going to be a positive 2/5, right? So it's no longer going to be negative. So flip and forget is what I call it. All right, so now we know that is 1 over 32 to the 2/5 power. Let's go ahead and focus on that. Well, now we know that 2 is my power, right? And 5 is my index, so I'll call it P and I. So now I can write it as 1 over, I have a radical, my index is now 5, my power is now 2. So now I can focus on the 5th power. So what number multiplied by itself 5 times gives me 32? All right, so basically I can rewrite this as 5th root of 32 raised to the 2nd power. So what number multiplied by itself 5 times gives you 32? So let's do it over here. So 32 breaks into 2 times 16, 2 times 8, that's a 2, that's a 2. 8 breaks into 2 times 4, 4 breaks into 2 times 2. So we got 5 2's. So basically this breaks into 1 over 5th root of 2 to the 5th, because we have, 5 2's here. And then squared. And so now the 5th cancels out with the 5th, so now the radical cancels out. So I got 2 squared down here. So I got 1 over 2 squared, and 2 squared is 4, so this is 1 over 4. All right, again, we have a negative exponent. Negative exponent means we flip and forget. So there's an invisible 1 down here. So we're going to go ahead and do flip and forget, F and F, however way you want to call it. Maybe you find a joke off of that. So we have 1 over 27. And then we flip the sign, so now it's going to be positive 2/3. So I'm just going to write it as 2/3. All right, so now we have a power of 2, power over index, an index of 3. So we can write this as 1 over radical. The index is 3, 27, the power is 2. I'm going to go ahead and write this out now as this raised to the second power, just to save us a little time. So a number that I multiplied by itself 3 times to get to 27. Again, we did this example kind of earlier, so I'm just going to go ahead and skip straight to it. It's going to be 3 to the third power, and then squared. So then the 3's cancel. So now I'm left with 1 over 3 squared, and 3 squared is 9. So I'm just going to write this out as 1 over 9. All right, go ahead and try the following examples. Pause the video, and I'll go ahead and go over the response. All right, so we got a negative exponent here, so which means we flip and forget. So this is going to be 25 over 1. So I'm going to flip that as 1 over 25, and then I'm going to forget the sign. So now it's going to be 1/2. Now I got a power of 1, and I got an index of 2. So I got 1 over radical, index is 2. Notice that I don't have to write the 2 there because it's going to be a square root. However, I'm just going to write the 2 there just to say that it's there. However, you don't have to write the 2, so I could just as easily rewrite this as 1 over square root of 25. Notice that these two are identical. With square roots, the 2 is invisible. So now we know that the square root of 25 is 5 because, 5 times 5 is 25. So then the square here and the invisible 2 basically cancel each other out, leaving you with 1/5. All right, so now for part B, we got 32 to the 2/5 power. No negative exponent required. So we have a radical. Again, we got power over index. So the index is 5, so we're doing a 5th root of 32. We're going to go ahead and raise this to the second power because that's our power here. So now a number that multiplies by itself 5 times to get to 32. We actually did that earlier, so I'm not going to spend too much time on that. It's going to be 2 to the 5th. And then the 5's cancel. So we got 2 squared, which is 4. All right, so now next we're going to talk about all about simplifying nth roots. How do we go about simplifying radicals? So there's a process to this, kind of an extensive process, but once you get the idea of some basic rules, it'll start making sense. So let's first talk about how to simplify something like this. So let's say we had cube root of x to the third power. So let's say we want to simplify that as much as possible. Well, we know that, so like what is this going to be equal to is what we want to find out. So you may go ahead and say, oh well, the 3 and the 3 cancel out. And in a sense, you will be right. The 3 and the 3 do cancel out. However, we want to be careful with some cases. Sometimes this won't always happen. In this case, it turns out that you can cancel out the 3's and you get the answer x. So in this case, it turns out that you can technically cancel out the 3's here and here and actually get x. But when will this not be the case? Well, we'll show you first why this is true. So let's plug in a number for x. Let's say x is equal to 1. And we plug that in. So then we have cube root of 1 to the third power. So then what's 1 to the third power? Well, we know that 1 to the third power is 1. And then a number that you can multiply by itself 3 times to get to 1. Well, that's simply going to be 1 because 1 times 1 times 1 times 1 is 1. So this is going to be 1. And notice that 1 is equal to x because that's what we said x was earlier. X was 1. So this works out. What about if x were -1? Let's plug that in. Well, let's see. We got cube root of -1 to the third power. Well, what's -1 to the third power? Well, we got -1 times -1 times -1. That's going to give us -1. So we have here cube root of -1. Again, if you had trouble following that thought, -1 to the third is simply -1 times -1 times -1. Two negatives is a positive, but then a positive and a negative is a negative. So this is -1. Now, so if we want the cube root of -1, well, what's a number that you multiply by itself 3 times to get to -1? Well, we just did it here, right? If we multiply -1 by itself 3 times, that gives you -1. So this is going to be -1. And it turns out that -1 is equal to the original x that we said earlier, right? It's equal to that. So there's no problem here. We know simply that cube root of x cubed is x. So this is tested and is verified. So we know this to be true. Let's look at another example, however, where this may not be true. So let's say you had 4th root of x to the 4th power. So now let's go ahead and plug in. We want to see if this is equal to x. Is this equal to x, as we would initially suppose? Well, if we plug in x equals 1, we get 4th root 1 to the 4th. Well, what's 1 to the 4th power? Well, 1 times 1 times 1 times 1 is 1. So this is going to be 4th root of 1. Well, what's the 4th root of 1? What's a number that you multiply by itself 4 times to get to 1? It's just going to be 1. 1 times 1 times 1 times 1, 4 times, it's going to be 1. And this is equal to x. So this actually works, right? X is equal to 1. That's what we said it was earlier. What about if we plug in -1? Well, then we have 4th root of -1 to the 4th. Right? What's -1 to the 4th power? Well, -1 to the 4th power, that's going to be, let's write it over here. -1 to the 4th power is -1 times -1 times -1 times -1. Well, two negatives make a positive, two negatives make a positive and a positive make a positive. So this is actually +1. So this is going to be 4th root of +1. And then what's the 4th root of +1? Well, we just said up here earlier that this is 1. Now notice that this is not equal to x. Why is it not equal to x? Because we said that x was equal to -1 originally. So this does not work. So this means that if you have an even power, it's not going to work because we had a 4 here. If you had an odd power, which is a 3, or 5, or 7, for instance, then this works. Well, how do we fix it? Well, the way to fix it is to make always make the x value that we plug in positive. So if I said that this were the absolute value of -1, then this would have worked, right? Because the absolute value of -1 is 1. So in order to make this work, we need to make sure that this is always going to become positive. Notice that we always get an answer that is positive when we do this. So in order to do this, we're going to change this into a absolute value of x. And this ensures that it stays positive. So moral of the story here is, if n is odd, so if n is odd, then this means the nth root of x to the n, you can cancel them out and say that it's x. If n is even, then this does not work. And what you have to do is, if you can't just simply cancel it out and call it x, you would have to call it absolute value of x. And this is the general rule of thumb that you want to keep in mind. All right, so when can we use this? So let's look at an example of when this is actually used. So let's look at the simple example of fourth root of x to the 8th times the cube root of y to the 6th. Okay, so at first glance this looks kind of complicated, but bear with me here. Let's just take one of these at a time. So let's look at the x part. So we know we have x to the 8th and we want to do fourth root. So what we need to do is, well, we have 8 of them, and the only way I can get this to cancel out is if I turn this 8 into a 4. So what I'm going to do is I'm going to break this into the fourth root of x to the 4th. So I'm going to break this into x to the 4th times x to the 4th. So x to the 4th and x to the 4th make x to the 8th, because we have a total of two 4s, which means we have a total of 8. And then I'm going to do the same thing for the y. I can break this into two sets of 3s, right? Y to the 3rd and y to the 3rd. Okay, hopefully you all agree that 3 and 3 makes 6 and 4 and 4 makes 8. So then what we can do is we can split the fourth root into two separate things. We could separate it into fourth root of x to the 4th, and then another fourth root of x to the 4th, and then another, we can split this into a cube root of y cubed, and then a cube root of y cubed. Now you notice that there's a bunch of those rules that we talked about, right? We have a cube root example, we have a fourth root example. So then how do we go about doing this? Well, we have here fourth root of x to the 4th. That can't just cancel out. If you were to cancel it out, then we would have to call it absolute value of x. And same deal here. That can cancel out only if you call it absolute value of x. And then here we have the cube root of y cubed. That can cancel out, leaving you with y, only because it's odd. If it were even, we would need the absolute value. Here, this can cancel out, leaving you with y. So basically what we have here is x times x is x squared. So we have absolute value of x squared times y squared. So we have two absolute values here. Oops. As such. And we can call this the final answer. Now you could say the absolute value of x squared is positive, but just to keep things consistent, I'm just going to leave the absolute value there, just to keep it consistent. So let's do more examples like this. So let's go ahead and simplify the radicals. So if we wanted to do the first radical, well, we have fifth root of 32m to the 15th. So let's kind of split this up into two separate things here. Let's go ahead and split this up into split the 32 up first. We know that the 32 can factor, right? So the 32 can factor into 2 times 16. 16 is 2 times 8. 8 is 2 times 4, and 4 is 2 times 2. So we have here, we have 5 2's. So we can basically rewrite this as the fifth root of 2 to the 5th, and I write it as 2 to the 5th only because I have a 5 there, which is what I want, times n to the 15th. So now we can split this up into two separate radicals, if you will. We could split into the fifth root of 2 to the 5th, and then the fifth root of m to the 15th. And then now these two cancel out, leaving you with 2. Notice that you can always cancel it out as long as you got a number here, but if that's a variable, then you're going to have to use the rule that we talked about earlier. Now for this, for the m, we have 15 m's in total, which means we have a total of 3 sets of 5, right? 3 times 5 is 15. So I can write this out as m to the 3rd times m to the 3rd times m to the 3rd, right? So I can basically write this out as m to the 3rd 5 times. 5 times 3 is 15. So if I write it this way, then I can see, well, okay, well, this cancels out, right? So I can say that this cancels out, and that leaves me with simply m to the third power. So I have 2 times m to the third power. Now, since the 5 is odd, I don't need to do the absolute value. Otherwise, I would have to include the absolute value here. Okay, let's look at another example. So this time we have an even index, which means that we're going to need an absolute value probably somehow, right? So let's break up 32 into 2 and 16, 2 and 8. Well, we actually broke that up earlier, didn't we? So let's just use the result that we had earlier. 32 is 2 to the 5th power, just to save us some time. So we have here 32 is the 4th root of 2 to the 5th power. And let's go ahead and rewrite this. X to the 20th, there are 5 4s in 20, right? So we can write this as x to the 5th raised to the 4th power, because I want the 4 to match that 4 there. And then for the y, I can write it as y squared to the, to the 4th power, because 4 times 2 is 8. And therefore they match, and so it works out perfectly. Okay, so now what I need to do here is notice that the 5s do not match here, right? And so what we need to do is we're going to split that 2 to the 5th as 2 to the 4th times 2, because 2 to the 4th times 2 to the 1 is 2 to the 5th. Okay, and then that will work out nicely for that purpose. All right, so now we got a 4th power here. So now let's split this up into several radicals. We got 2 to the 4th. We got the 4th root of just 2, the number 2. We got the 4th root of x to the 5th raised to the 4th. And then lastly, x to the 4th root of y squared to the 4th. So now these simply cancel nicely. So the radical cancels, leaving me with 2. Now this does not cancel because this is a 1, right? And there's nothing else I can do here. So I'm just going to leave this as the 4th root of 2. There's nothing wrong with leaving it as a radical. It just means that you have a decimal. So there's nothing I can do there. Now for this, I got a 4 here, so I can cancel that 4 on the outside with this radical. So that leaves me with x to the 5th. But remember, I need to include the absolute value here. So this is going to be the absolute value of x to the 5th. All right, and then for the y squared, the 4th cancels out, leaving me with y squared. And then I just got to make sure that I include the absolute value. Now technically it doesn't matter if you include the absolute value for the y squared, because y squared is always going to be positive. However, I'm just going to leave it like that, just to be consistent. And throughout these problems, I'm going to always leave it on there, even though technically you do not need the absolute value for the y squared, because it's always going to be positive, so it doesn't really matter. So in this case, you can combine these two absolute values and combine it as x to the 5th y squared, like this. So either one of these is correct. Okay, so it doesn't matter which one you use. They're both the correct answer. Okay, so this or that is perfectly fine, or you can just ignore the absolute value on the y squared. All right, go ahead and pause the video, give these problems a try. All right, so we want to simplify each expression. So we got a cube root and we got -8. So let's go ahead and break down the 8 part. So, well, we know that 8 is 2 times 4 and 4 is 2 times 2. So really this is just 2 to the 3rd. So we have here the cube root, -2 to the 3rd. And then we have a cubed, right? So a cubed, there's nothing that we can really do there because that's a 3 and that's a 3, so this is perfect. Now for the b to the 9th, there's three 3's in 9, right? So I can write this as b to the 3rd times 3. So therefore the 3's will cancel out later. So now we're going to split this into the separate radicals. So I got negative 2 to the third, then cube root of a to the third, and then cube root of b to the third cubed. And then now notice that the cube roots here cancel, leaving me with negative 2. The cube roots here cancel, leaving me with a. Now since this is odd, I can leave it as a, and I don't have to write it as absolute value of a. Same thing here, since this is cubed and that's odd, I can leave it as b to the third and not have to worry about the absolute value. Alright, so let's look at this one. This is even, so I will have to worry about the absolute value at some point. You know, as a rule of thumb, just leave it as absolute value if it's even. So we have here 4th root of 256. So we definitely need to break this number down. So half of 256 is 128. Half of 128 is 64. Half of 64 is 32, and half of 32 is 16. Half of 16 is 8, half of 2 is 4, and half of 4 is 2. All right, so basically we have 4 2's here, and we got 4 2's here. So basically it's 2 to the 4th and 2 to the 4th. So I'm going to write it as such. I'm going to write this as, since it's 4th power here, 2 to the 4th times 2 to the 4th. I got 2 sets of 4's. For the x squared, I have, I can write that in terms of 4 as 3 times 4. So 3 to the 4th power. And then 24, I can write that in terms of 4 as 6 power raised to the 4th power, like that. 4 times 6 is 24. So now I got, I have I can split this up into two separate things. I got 4th root of 2 to the 4th, 4th root of 2 to the 4th. I got the 4th root of x cubed to the 4th, and then I got the 4th root of y to the 6th to the 4th. So now the 4's cancel here, 4's cancel here. Now since this is a number, it doesn't matter. I mean, since it's a positive number, it doesn't matter that you did the absolute value. It's just going to be, 2. If this were a negative 2, then you would make it into a positive 2, right? So technically, just to be consistent, I'm just going to say, this is going to be absolute value of 2, but the absolute value of 2 is 2. So it's just going to be 2 times 2. And then since this is a variable, we have 4's canceling. Since we have an even root, this becomes absolute value of x cubed. And then this is 4, that's 4's cancel. Since this is even radical of 4, we need a absolute value. And 2 times 2 is 4, so we got 4, and then I'm going to combine these under one absolute value. Okay, so this is the answer, or that is the answer. Either one of those suffices. Actually, I would probably prefer this to be written as 4, and then those separately. So let's write this out as 4. So either of these responses are good. Alright guys, that's it for the video. I know there was a lot going on with radicals and rational exponents, but I hope you took something from this video, and I'll see you in the next one.